Welcome to The Deep Dive. Today we're actually tearing down the delivery layer of the internet.
Which is, honestly, it's a critical topic for anyone building modern applications right now.
Yeah, absolutely. Our mission for this session is to explore a really fascinating architectural breakdown from a tech blog. It's called The Secret Life of AWS, written by Aaron Rose.
Right.
And we're going to look specifically at how engineers manipulate network geography, basically how they bypass the physical limitations of the speed of light so that data hits your screen instantly no matter where you are sitting on the globe.
Because it's a scenario that highlights a very common blind spot in system architecture. We spend so much time, obsessing over back-end compute optimization
Oh, for sure.
that we just completely neglect the final physical journey of the data to the user.
Exactly. So to set the baseline here, our source material follows a software engineer named Timothy. And Timothy is analyzing an AWS X-ray service map.
Which is a great tool.
Yeah, it gives him this comprehensive telemetry dashboard showing exactly how fast his application is executing. And looking at his back-end compute layer, Timothy has built, a perfectly tuned machine.
He really has.
His microservices, the step functions orchestrating his complex workflows, his DynamoDB database queries, they are all firing seamlessly. We are talking about back-end responses returning in single-digit milliseconds.
Single digits.
Yeah.
Which is incredible, but, and this is where it gets interesting, there is a glaring paradox in his telemetry.
Right.
His back-end compute is highly optimized, but his front-end metrics, the data showing the actual load times experienced by the end user navigating the app, they tell a completely different, highly frustrating story.
The dashboard reveals this massive geographic discrepancy. Timothy actually points this out to another engineer in the story named Margaret. The users who are physically located in Virginia, they're receiving their product images and front-end JavaScript files in about 40 milliseconds.
Which is a highly performant, essentially instantaneous experience.
Right. But for users in London and Tokyo, it is taking an agonizing 800 plus milliseconds just to download those exact same files.
And we know that 800 milliseconds in modern web application standards is, well, it's a death sentence for user retention.
It feels broken.
It feels incredibly sluggish, yeah. So Margaret steps in to diagnose this discrepancy, and she goes straight to the storage architecture. She looks at the deployment diagram and asks where the static assets are actually hosted.
And Timothy confirms they are sitting in an Amazon S3 bucket.
Crucially, that bucket is provisioned in the S East 1 region.
Right, which is physically located in data centers in Northern Virginia, which obviously explains the 40 millisecond load times for the Virginia users. They're requesting files that are practically right down the street from it.
Exactly.
But for a user sitting in, say, a cafe in Tokyo, that request has a massive physical journey. It has to navigate through local Japanese internet service providers.
Find a transit path.
Yeah, find a transit path across the Pacific Ocean, hit the North American network backbone, navigate all the way to that specific S3 bucket in Virginia, and then the image payload has to make that entire journey in reverse.
Margaret diagnoses this immediately as a delivery layer failure. She basically tells Timothy that he is simply paying the ultimate latency tax for physical distance.
The speed of light is undefeated.
It really is. His compute layer is flawless, but he's relying on long-haul transit across the public internet to deliver his front-end assets. So her proposed solution is to implement a content delivery network, or a CDN.
And since they're operating within the Amazon ecosystem, they architect this using AWS's native CDN service, which is Amazon CloudFront.
Right.
Okay, let's unpack this. We know the goal of a CDN is to fix this geographic delay, but how does CloudFront actually integrate into this existing architecture?
Well, the implementation starts by defining the definitive source of truth for the application's data. When Margaret configures the new CloudFront distribution in the AWS console, the first parameter she sets is the origin.
The origin.
Yeah, and the origin is exactly what it sounds like. It's the absolute starting point where the authoritative original files live. In this specific architecture, the origin is Timothy's existing S3 bucket in Virginia.
Now, a major takeaway from the source material regarding this setup is the security posture. Because if the S3 bucket is the origin, how do we prevent users or, malicious actors from just bypassing the CDN entirely and querying that bucket directly?
That is a critical architectural consideration. You never want to leave your origin exposed to the unpredictable public internet.
Because if they bypass it,
If users can bypass your delivery network, they can hammer your source bucket directly. That completely defeats the purpose of the CDN, and it can lead to massive cost overruns or even a denial of service situation.
Which is a nightmare.
Absolute nightmare. So to mitigate this, Margaret implements a security protocol called Origin Access Control, or OAC.
How does Origin Access Control actually function at the bucket level?
Think of OAC as a highly specialized cryptographic bouncer for your S3 bucket.
Okay, I like that.
Margaret modifies the bucket policy using OAC so that the bucket categorically rejects all public web traffic, doesn't matter who is asking. The bucket is configured to only accept read requests that carry a specific authentication signature, proving they originated from their designated CloudFront distribution.
So it completely locks down the origin. The data is secured in Virginia, and the only ingress point is through CloudFront.
Precisely.
But that still leaves the core problem unresolved, right? The authoritative data is still physically sitting in a data center in Virginia. How does CloudFront actually eliminate that 800 millisecond delay for the user in Tokyo?
This is where we leverage the global network infrastructure. See, CloudFront doesn't operate from a single centralized location. It's a distributed system utilizing hundreds of physical AWS data centers scattered all across the globe.
The edge locations.
Yes. In CDN terminology, these distributed data centers are called edge locations.
So instead of forcing every user worldwide to make that long-haul network trek to Virginia, CloudFront is pushing the data out to these edge locations.
Exactly. And the key to making this work seamlessly for the end user is the underlying DNS routing. Margaret breaks down the mechanics of this for Timothy. When our user in Tokyo types the website URL into their browser and requests that product image, the network routing does not attempt to send that request to North America.
It intercepts it.
Right. The DNS infrastructure intercepts that request and automatically resolves it to the IP address of the CloudFront edge location that is geographically and topographically closest to that user right there in Japan.
So the request is handled locally, and this brings us to the core performance mechanism of the entire architecture, the cache hit.
The holy grail of CDNs.
If that local edge location in Tokyo evaluates the request and realizes it already has a copy of that specific product image stored on its local hard drives, it serves that file back to the user immediately.
And that cache hit is the ultimate goal of the delivery layer. Because the edge location had the file ready to go, the physical distance the data had to travel was reduced from thousands of miles across an ocean to just a few miles down the road.
Which is wild when you think about it.
It is. Margaret pulls up the new telemetry data for Timothy, and the impact is staggering. By achieving a cache hit at the local edge location, the latency for the Tokyo user drops from over 800 milliseconds down to under 20 milliseconds.
Under 20 milliseconds. I mean, they are now experiencing faster load times than the local Virginia users were getting on the raw S3 bucket.
It completely levels the playing field globally.
It really does. But I want to explore a very specific constraint that Timothy brings up in the story, and it's something you listening right now might be analyzing for your own applications. Is this edge location caching mechanism only viable for static files? Like, does a CDN only provide value for things like JPEG, CSS, and basic JavaScript files?
That is a vital question, because modern web applications are rarely just static brochures anymore.
Right.
Margaret clarifies to Timothy that CloudFront's utility extends far beyond static asset caching. It also provides profound performance benefits for dynamic API calls.
Okay, consider a highly dynamic stateful interaction, like a checkout API, where a user is submitting payment information and finalizing a cart. That type of request is unique to that specific user at that specific millisecond.
Yeah.
You inherently cannot cache a live credit card transaction or an inventory decrement. The edge location can't just serve a saved copy of someone else's checkout. So if we can't cache the payload, how does the CDN accelerate a dynamic request?
It comes down to fundamentally altering the network transit path. We have to look at how the internet normally routes dynamic traffic.
Okay.
Without a CDN, a dynamic POST request from Tokyo to an API gateway in Virginia has to traverse the public internet. The public internet relies on standard BGP routing, meaning that requests will bounce through various autonomous systems, third-party transit providers, peering exchanges.
It's a mess.
It is highly unpredictable. It's prone to congestion and requires multiple network hops. It's the digital equivalent of taking local backroads during rush hour.
So you are basically at the mercy of whatever network weather exists between Japan and the US at that exact moment.
Right. How does CloudFront change that routing behavior?
Well, when you route that dynamic API call through CloudFront, the user's request is ingested at the local Tokyo edge location. And the critical performance gain happens right there at ingestion. The complex TLS handshake, the cryptographic back and forth required to establish a secure connection that is negotiated locally in Japan.
Oh, which saves massive amounts of latency right off the bat.
Exactly. Once ingested, CloudFront takes that payload and rockets it across AWS's own private, dedicated global fiber network backbone.
It completely bypasses the unpredictable public internet.
Yes. It places the request onto a private, highly optimized superhighway that routes directly to the application's backend in Virginia. So even though the data cannot be cached, the delivery path is dramatically shortened and stabilized. That results in significantly faster and more reliable dynamic API performance.
That is a phenomenal architectural insight. The edge location isn't just a storage locker, it is a high-speed on-ramp to a private global network.
That's a great way to put it. Okay, let's pivot back to the static files, because here's where it gets really interesting regarding the lifecycle of the data. We established how incredibly fast a cache hit is. But let's look at the inverse scenario. What happens if our user in Tokyo requests a brand new product image, an asset that the Tokyo edge location has never seen before and does not currently hold in its local storage?
In CDN architecture, this is known as a cache miss. And the protocol for handling a cache miss is highly automated. The edge location receives the HTTP request, evaluates its local cache registry, and determines that the requested file is missing.
So it doesn't have it.
Right. So instantly, it utilizes that same dedicated high-speed connection we just discussed to reach straight back to the origin, the secured S3 bucket in Virginia.
So a cache miss means we still have to pay the latency tax to cross the ocean and hit the origin.
We do, but only for that initial request. The edge location pulls the original image from the S3 bucket in Virginia and serves it back to the user in Tokyo. However, simultaneously, the edge location writes a copy of that image to its own local storage. This means that while the very first user who requested the file experiences that slight latency delay, the application has now adapted. The very next user in Tokyo who requests that exact same product image will hit the local storage and experience a sub-20 millisecond cache hit.
The network is dynamically caching based on the specific localized demand of the users in that geographic region. That's brilliant. But Timothy raises a very practical business concern regarding this behavior.
He does.
What happens when the underlying data changes? Suppose the marketing team decides to update a specific product image. They adjust the color grading or update the packaging. You absolutely do not want your global edge locations continually serving the old, outdated version of that image simply because they saved a local copy of it during a previous request.
That is the fundamental challenge of distributed caching. You need a reliable mechanism to control data freshness and dictate exactly how long an edge location is allowed to trust its local copy.
Right.
Margaret explains that this behavior is managed using a configuration called time to live, commonly referred to as TTL.
How does TTL function at a technical level between the origin and the edge?
TTL is essentially an HTTP header configuration, specifically the cache control header. It dictates the lifespan of a cached object. It tells the CloudFront edge location exactly how many seconds it is permitted to keep a file in its local cache before it must consider that file expired.
Okay.
In the source material, Margaret provides a concrete configuration example. She suggests setting a TTL of 86,400 seconds.
Which translates to exactly 24 hours.
Correct. With a TTL of 86,400 seconds, the Tokyo edge location will confidently serve its locally cached copy of that product image for a full 24 hours. During that window, it will not communicate with the origin in Virginia at all regarding that file. It will simply absorb the traffic and serve cache hits.
But the millisecond that 24-hour timer expires, the cached file is flagged as stale.
Yes.
And what is the protocol for the very next request that comes in after that timer expires?
The edge location treats it essentially as a cache miss. The next time a Tokyo user requests that image, the edge location recognizes the expiration flag. It is forced to reach back across the network to the origin in Virginia, validate the file, fetch the newest, most up-to-date version from the S3 bucket, serve it to the user.
And then restart the clock.
Exactly. Restart that 24-hour TTL clock on the newly cached version.
That provides a very predictable cadence for standard asset updates. Waiting 24 hours for a new product photo to naturally propagate across the global network is usually an acceptable timeline.
Usually, yes.
But Timothy poses a highly relatable scenario that stress tests this architecture. What if an engineer makes a critical error? Suppose someone accidentally uploads the wrong company logo or publishes an image containing sensitive, embargoed information.
That's a panic moment.
Oh, massive panic. You need that asset removed from the public-facing application globally, and you need it done immediately. You cannot afford to wait 24 hours for the TTL timer to naturally expire across hundreds of distributed beta centers.
It is an operational nightmare,
Right.
and it requires a specific strategy. Margaret addresses this by outlining the standard architectural best practice for urgent updates, which relies on a concept called file versioning.
How does file versioning allow us to bypass that strict 24-hour TTL lock?
It works by manipulating how the CDN identifies files. CloudFront, like most caches, uses the exact URL path of the file name as the unique cache key. If the erroneous file was named logo.png, the edge locations are holding on to that specific cache key for 24 hours.
Right.
To utilize file versioning, you do not go into the S3 bucket and attempt to overwrite the original file. Instead, you upload the corrected accurate image as a brand new file with a unique name. For example, logov2.png. You then update your front-end code to request this new file name.
So because the file name is fundamentally different, the cache key changes.
Exactly. When the updated application requests logov2.png, the CloudFront edge locations evaluate their storage and realize they have never seen this specific cache key before. It registers as an instant cache miss simultaneously across the entire global network. Every edge location is forced to immediately fetch the new file from the origin, completely sidestepping the 24-hour TTL wait that is still ticking away on the old abandoned logo.pn file.
It is an incredibly elegant solution because you are just feeding the network a completely novel request. But this leads to one final architectural question. What if you are in a constrained environment where you simply cannot update the front-end code to change the file name? What if you absolutely must purge a file from the global cache immediately while retaining its original URL? Do we have an override mechanism for that?
We do. When file versioning is structurally impossible, Margaret introduces the administrative override, the cache invalidation. An invalidation is a manual command issued through the AWS console or the API. You specify the exact file path you need, purge for instance, images logo.png-, and CloudFront executes the command.
What actually happens across the network when that invalidation command is triggered?
CloudFront broadcasts a high-priority purge directive to every single edge location worldwide. It essentially forces hundreds of distributed systems to instantly scan their local storage, locate any cached copies associated with that specific path, and forcefully delete them before the TTL expires.
But the source material is very clear that this is not the preferred method for managing updates. Why is that?
I would caution you, just as Margaret cautioned Timothy, that invalidations are strictly an emergency mechanism. They're computationally expensive, and they take time to physically propagate across a massive global infrastructure.
Right.
More importantly, because it requires significant overhead to execute a global purge, AWS limits the number of free invalidations you can run and actively charges you money to execute them at scale.
Oh, wow.
Relying on invalidations as a standard deployment strategy will quickly result in architectural bottlenecks and inflated cloud bills. That is why file versioning is the gold standard, leaving invalidations strictly as the break glass in case of emergency option.
It is the absolute last resort. So tracing Timothy's journey through this architectural overhaul, he implements Margaret's design, he provisions the CloudFront distribution, he secures the S-East-1 S3 bucket using origin access control, he tunes his TTL headers for optimal caching, and establishes a file versioning protocol for his front-end deployments. Finally, he monitors his X-ray telemetry dashboard to measure the impact.
And the telemetry validates the architecture entirely. The agonizing 800 millisecond load times for the users in London and Tokyo completely disappear. The delivery layer latency drops to match the performance of the local users in Virginia.
As the author points out, the application has evolved from just being functional to being truly globally distributed. So what does this all mean for us? When we synthesize this deep dive, the most compelling takeaway is a fundamental shift in how we perceive cloud computing.
I completely agree.
The industry often abstracts the cloud as an omnipresent magical entity, but it is intensely physical. It is constrained by miles of subsea fiber optic cables, network transit protocols, and ultimately, the immutable speed of light. AWS CloudFront and its network of edge locations do not break the laws of physics. They simply manipulate network geography in your favor.
Exactly. They move the starting line of the data transfer right next to the finish line.
That is the exact architectural reality.
And for you listening, I highly encourage you to apply this perspective to your own daily interactions. The next time you are traveling abroad, perhaps opening a familiar web application in a hotel in Tokyo or a cafe in London, pay attention to that instant load screen. You are not just witnessing efficient front-end code, you are directly benefiting from this invisible, highly orchestrated global infrastructure. You are interacting with lockdown origins, distributed edge locations, and localized cache hits, all working in tandem to conquer physical distance.
It is a phenomenal feat of modern engineering hiding just behind the glass of your screen. And I want to leave you with one final, slightly provocative thought to mull over as we wrap up today's session. We have spent this deep dive analyzing how global content delivery networks seamlessly bridge oceans in mere milliseconds by locally storing data that they think we are going to need based on regional demand.
Right.
If they have perfected that predictive distribution, how much of our everyday digital experience, from the articles we read to the media we consume, is already being anticipated, cached, and staged in a physical data center just down the road from us?
Before we even ask for it.
Exactly. Before we even decide to click a button, think about that the next time the internet feels like it is reading your mind. Thank you so much for joining us on this deep dive. We will catch you next time.